Hi guys, John the Quant here. This is week 2 of the free data science internship bootcamp series. Now this series is designed to take you from knowing nothing about data science to being ready to explore a data career as an intern. And this video series closely follows the in-person data science bootcamp that I guide at the Community College of Aurora in Aurora, Colorado. Now this is week 2. If you did not start with week 1, I highly recommend that you start with week 1. A link should appear, up here somewhere, and there will also be a link in the description. This week is all about probability and statistics. But don't worry, we're not going to be doing any of the math by hand. We're going to let the computer do all the tedious parts. Now what's important here is that you understand what the numbers mean, why they're important, and what probability distributions look like. If you can interpret the numbers and figure out what kind of distribution you are looking at, you can figure out how to work with the data, and you can explain what you're doing and why. So what we learn in this week is going to be super important for everything that comes after, so do not skip it and do not half-ass it. Let's get started.
All right, we're looking at this notebook. Here we've got kind of the usual imports, pandas, numpy, and matplotlib. I've included a new one that is import seaborn as SNS. You might need to install the seaborn package. I think you can figure out how to do that. Seaborn makes some really nice looking plots, and we're going to look at a lot of plots here. I've also imported the statistics package. This comes already installed inside Python, and I do use it a couple of times, but it's not super important. I don't know that you need it. And we've just loaded the data and made all of the columns lowercase. This is the same diabetes data that we worked with in the mini project from last week. Here we go. This is a histogram. You're going to be looking at a lot of histograms throughout this bootcamp and probably beyond. And reading a histogram is a really valuable skill, and you can learn a lot from this single chart. So, you see this bar? On the x-axis, it goes from 0 to 10, and on the y-axis, it goes up to 400. So, in this data set, they had 400 people, ages between 0 and 10. That's what this means. They had 1,100 people here, between 10 and 20 years old. And then let's pick another one. Between 60 and 70 years old, they had about 100 people. So how many people were there between 70 and 80? All right, good job. You guys said 700, I assume. Okay, so what a histogram tells us is where is most of the data? Or to put it another way, which values are common in the data? All right, 10 to 20 years old is common in this data set. 60 to 70 is not common. Later we're going to use histograms to answer what is the shape of our data. But now let's look at examples from the diabetes data that we've been looking at. In this code cell, I've created a set of charts, one for each column of the data, and it cycles through the columns of the data frame and makes a histogram of each column. So I've got incalls is the number of columns, or the shape, the first spot of the shape of the data set, and then I'm making a bunch of subplots, cycling through and making a histogram for each plot. As you can see here, I've got one for pregnancies, and one for glucose, and so on. Now these won't be quite as easy to read as our example, but they do tell us the same thing. So let's look at this first one. It's important to notice that a lot of these people had 0 pregnancies. Can I make this bigger? There we go. All right, it's a lot of people had 0 pregnancies. But a couple of people had like 12 pregnancies, or 15, or even 17.5. All right, so in the second one, the important things to see are that people had generally between like 50 and about 200 as a glucose reading, but most people actually were between 100 and like 125 right in here. And some people had 0 as a glucose reading. So we might want to investigate and see if that's an error in the data or if people really had 0 as a blood glucose reading. I'm not sure that that's medically possible without being dead. Blood pressure has kind of the same thing as the glucose, where most people here it's between like 60 and 80, but there's a bunch of people that had 0. So maybe the doctors just like entered 0 if they didn't know. Someone with 0 blood pressure is definitely dead, I'm pretty sure. So it doesn't matter if you have diabetes if your blood isn't moving. Skin thickness shows us another similar thing where there's like a hump here around 30. but there's a tall bar at 0. We can see the same thing kind of with insulin, but it's a little harder to tell if there's like a definite hump here or not. Humps are important. We're going to talk about histogram humps later in the video. BMI has a definite hump. The diabetes pedigree function and age histograms, they don't have those tall bars around 0. See? But they do kind of have humps. It definitely looks like the doctors just entered 0 for tests that they didn't do. And if we were to fit a model to predict whether people have diabetes, like that would be a big problem. All these zeros that don't mean anything. So let's look at the last one real quick. The target column. Here it's called outcome. Notice how there are just 2 bars at 0 and 1. Now that's because this column only has zeros and ones, where 0 means they don't have diabetes and 1 means they do have diabetes. You could use a bar chart instead of a histogram for a feature like this, and you probably technically should, but as you can see, the histogram creates a bar chart anyway. So a histogram does work. In features like this, it's important to think, the important thing is to look for the difference in the height of the bars. Okay, the 0 bar is about twice as tall as the 1 bar, which tells us that our data has twice as many non-diabetics as diabetics. And this might matter when we start using machine learning on the data. So that's how you read a histogram. It's important to look for anomalies, like the tall bars at 0, and it's important to look for humps, like this hump here around, 32. And it's important to notice the shape of the data. It drops down like this. And when your data is binary, like this one, it's important to compare the size of the bars. Now, when we're making predictions, we're going to use measures of center a lot. Now, a measure of center answers the question, where is the data, mostly? Think of the data as a target, okay? Sharpshooters care very much about the center because that's what they're trying to hit. Data professionals care about the center of the data for kind of the same reason. When you make a prediction, you're trying to hit a small target right in the center. However, when sharpshooters look at a target, they can tell where the center is. It's pretty obvious. It's right in the middle. But let's try it with data. So have a look at this age histogram and tell me, where is the center? Well, maybe it's like right here in the middle. Or maybe the center's over here where it's like this bar is really tall. Or maybe the center's right here at the top of the hump. Or maybe the center is somewhere like between 30 and 40, somewhere between the hump and the middle. So where is the center? Well, any of those interpretations of center is valid. So here's the same histogram where here's the same histogram with 4 different ways to interpret center on it. And any of these is valid, but this is the order of most common to least common, and that's the order we're going to talk about then. So the mean is the black line here. Median is the red line. Mode is where the tallest bar is. And the middle is right in the middle. We're going to talk about the mean first. So mean is another word for average. And there are a lot of ways to calculate an average, but the only one we're going to worry about is the arithmetic average. So you just add up all the values and then divide by the number of values. The mean is often considered the value that best represents all of the data, and the mean has some good statistical properties that we're not going to get into that makes it ideal for traditional modeling. Most importantly, it is an unbiased estimator, and when we say unbiased, what we mean is that the average of a random sample, like this, should be the same as the average of the total population. So here our average is like, 33 or something. So you would expect the average of all women, average age, to be about 33. Even if they're not in our data set, you would expect the entire population of women to be about 33 years old. Or, say you wanted to know the average height of a person in your city. So you could randomly grab 20 people and measure their heights, and the average or mean of those 20 people will be close to the average height of everyone in the city. We are going to talk more about unbiasedness in week 4. It is an important idea for modeling in general. So let's have a look at the mean of a couple of our columns and talk about them. The mean works great when your data is symmetrical, like BMI, but not so great when the data is skewed, like age. Skewed means that some of the observations are really far in one direction. Like, look here, we see that most people are in their 20s, but there are some people all the way up in their 80s, and the number of people kind of dissipates as we go from 20 to 80. So for skewness, we're looking for like a slope, like we see here, like you're going down this mountain, right? Age is pretty heavily skewed to the right, and right skewed means that the long tail is on the right. It would be left skewed if the tail was over here on the left. The reason skewness is bad for the mean is that these outlier values, these really high ages, can move the mean really far. And when that happens, you can end up predicting numbers that are not similar to most people. So with age here, again, the mean is about 33 years, but we know that most people are actually in their 20s. So if we use the mean as the center, we would expect people to be older than they really are. The next measure of center is the median, and this is the easiest and most common way to overcome that shortcoming of the mean. So the median is the middle value, all right? We take all of the numbers and we put them in order like this, and we find the middle one. You don't have to do it by hand here, all right? It's 29. Handily, there's a dot median function that just kind of does all the work for you, spits out 29. And 29, as we look over here, 29 is actually a lot closer to most people's ages than 33 is. So when we talk about age, the median might actually be a better measure of center than the mean, depending on what you're doing. So when the data is asymmetrical like this, all right, the median will be closer to the taller bars where most of the observations are. But when your data is symmetrical like BMI, your median and your mean should be very close together. In this case, they're almost exactly the same, see? The mean is 31.99 and the median is 32. Median works really well in most situations, actually, but it isn't unbiased, so we can't assume that the median of a sample is going to be close to the median of the whole population. What this means is, in general, we can use the mean with only like 35 data points, but we need a lot more data points to use the median. Now, most of the time, you will have a lot more, so it's not that big a deal. The basic rule is that it's better to use the mean when the data is symmetrically distributed, and better to use the median when the data is skewed. Next week, we're going to look at ways to make the data be more symmetrical, and once it's symmetrical, you can just use the mean. The mode here, mode means it is the most common value. So in a histogram like this, it's the point where the tallest bar is. So in age, it's like somewhere in the low 20s. It says here 22. In BMI, it's in the low 30s. It's actually 32 as well. So up here, this means that more people in our data are 22 years old than any other age. And down here, it means that more people have a BMI of 32 than any other value. If you were asked to predict a person's age at random, you would be more likely to be exactly correct if you guessed, say, 22, but you would also be pretty far off most of the time, and you could even be 60 years off if the person is in their 80s. Whereas if you see, when your data is symmetrical, the mean, median, and mode all kind of show up in the middle. The middle here is the average of the biggest and smallest value. So you add the biggest value to the smallest value and divide by 2. That's what this line does. When you use the middle as a prediction, you won't ever be more than half of the range off. And this isn't usually optimal, but sometimes it can be useful. I think the most interesting thing about the middle is that when you're making a model, you want the middle and the mean and the median and the mode to all be as close together as possible. Now, when those three numbers are really close together, it tells you that the model is going to be accurate in a statistical sense. We have strong mathematical reasons to believe that the model is going to be the best it can be. So here with BMI, it's symmetric, and you can see that the mean, median, mode, and middle are all pretty close together. So this is what we want when we're trying to make predictions. This one is going to be much harder to make predictions for, and you're going to have to choose things that have trade-offs. Those are our 4 measures of center, okay? Mean, median, mode, and middle. So we can use those to make predictions, but in order to understand our predictions, we need what are called measures of deviation. Now, deviation is a fancy word, and what we care about here is how far is the rest of the data from the center. While the measures of center helped us figure out where the center of the data is, the measure of deviation is going to tell us how much the data is spread out. The first thing I hope you're thinking is that the answer to how far away is the rest of the data from the center is going to depend on which measure of center you use. And each measure of center above has a measure of deviation that is most commonly used along with that measure of center. But before we really get into those common measures, we need to talk about variance. Variance is very important from a mathematical perspective, but it's a little hard to intuitively understand. The first thing you need to understand is that higher variance means that the points are, on average, farther away from the mean. The calculation looks weird, so let's look at it visually. Here is a number line of the age column, zoomed in so we can see it. So each point is someone's age. The red line here is the mean. So to calculate the variance, what we do is we get the distance from each of these dots, get the distance from a dot to the red line, then you draw a square. And you draw those squares for each of the data points. Then what you're going to do is you're going to find the average area of all of the squares. So what you do is you draw all the squares, add up the area of the squares, and then divide it by the number of squares. So it might seem like us to be kind of a stupid way of doing it. I mean, why draw squares? Well, there are three reasons. First, the area of a square is always positive. So if the data is symmetrical, the mean is near the middle, and if we just add up the difference between all the data points in the mean, they'll cancel each other out, but not if we make them into squares first. Second, it's really easy to write in mathematical notation. It looks like this. Don't worry too much about knowing what all these symbols mean, just recognize that it's pretty easy to write. Third, it turns out that when you do it this way, a lot of other math ends up being much easier. So most importantly, the math for linear regression, which we will be talking about in week 4, is pretty easy when you use the squares and almost impossible if you do it any other way. You need to have an idea of what variance is, but you will not need to calculate it, and you will only use it in a few specific situations. Most of the time, when data scientists are working with variance, we're trying to minimize it. If we need to, we can get the variance easily in Python using .var. Here we see that the variance of age is about 138, and the variance of BMI is about 62. So let's look back at the histograms. Would you have guessed that age has twice as much, spread as BMI? They both have a range of about 60. Would you have guessed that age was twice as much spread out as BMI? So when it comes to data, you can't always trust your eyes or your instincts. Math sees things that we can't, and you need to trust the math. Also notice down here that the units are squared. Okay, you cannot compare variance to the original data. It's on a different scale. You cannot compare variance to the original data. Standard deviation is by far the most common measure of deviation. Standard deviation is just the square root of the variance. So if we were doing it by hand, we would calculate the variance up here, and then we would just take the square root. Now, this makes the standard deviation on the same scale as the original data, so you can compare the standard deviation to the original data. Notice how the units here are not squared anymore. That's the important part of standard deviation. Here we see that the average age is 33, and the standard deviation is about 12. So we could say something like the average person is 33 years old plus or minus 12 years. Or you can see that the mean of BMI is about 32 and the standard deviation is about 8. So you could say the average BMI is 32 plus or minus 8. And people know what that means. You can say that sentence and people will understand. Standard deviation is often the best measure of deviation to use with the mean because people understand it so well. Here's a histogram. This is the mean of 33 plus or minus 12. And here is BMI. Here's the mean of 33 plus or minus 8. 32. There we go. Plus or minus 8. All right, so remember the median. To find the median, we put all the numbers in order like this. And we found the middle. So now let's take the first half of the numbers and find the middle of that. And we'll take the second half of the numbers and find the middle of that. The median is called the second quartile. And if we take only the first half of the numbers and get the median of that, that is called the first quartile. And if we take only the second half of the numbers and get the median of that, that is called the third quartile. So the interquartile range is just the difference between the third quartile and the first quartile. And this tells us the total width of the middle half of the data. So here's all of the calculations to find the interquartile range of the age column. All right, to get the first quartile, you use the np.percentile function and tell it the 25th percentile. And then for quartile 3, you do the same thing, but it's the 75th percentile. Median would be the 50th percentile. Now you can just take the difference between the first and third quartiles there, and you see that the interquartile range of age is 17 years. But we can't use interquartile range the same way we use standard deviation. We can't really say plus or minus 17. But we can use the first and third quartiles to say the average person is between 24 and 41 years old. That's a slightly tighter interval than we could actually say with the standard deviation, and business people will probably like that better. Interquartile range is good when the median is the most important measure of center. Here is age with the first and third quartiles. So you can see that they're not symmetric because the data is not symmetric. And that can be really helpful. It tells you about half of everybody in this data set was between, 24 and 41 years old. And then here's the same thing with BMI, where it actually is very symmetric because the data is symmetric, and about half of all people are between 27 and 36 years old. Next measure of deviation is range. Range is super easy. It's just the difference between the highest value and the lowest value. This gives you an idea of the maximum actual spread of the data. So when making a prediction, the range kind of tells you what is the biggest error that you could possibly make. This can be helpful when deciding whether to use the mode as a measure of center. When the range is small, you can predict the most likely value and you won't be too far off, but sometimes the range will be too wide and using the mode will lead to really big errors. Like here, if we were to use the mode of 22, our range is about 60. Yeah, it's 60. So, like, the largest error we could make is 59 years, which is a big error. Now, if all of our data points were between 20 and 25, and we were to predict the mode of 22, then, the maximum error we could get would be 4 years, and maybe that's not a big deal. Now, the range of BMI is 67.1. The mode is almost exactly the same as the median and the mean. So the largest error you could get here would be about 35 years. Last measure of deviation we're going to talk about is what I call the half range. I don't know if this is a technical term or if it has a technical name. I'm calling it the half range. So half the range is half of the range. It is the difference between the middle and the highest or lowest value. You can use it the same way you would use the range. So if you use the middle as a measure of center, the half range will tell you what is the biggest error you're likely to make. There are times when what you want most is to minimize the maximum error. When error causes something really bad, like say you're predicting on average how much a car insurance company is going to have to end up paying out. Now, if you're really far off, your whole company is going to go broke. So you really need to constrain the maximum error, and half range is a great way to do that. This is the middle of age and the half range. The largest error you could get when using the middle to predict age would be 30 years. Same thing for BMI. The largest error you could get when using the middle to predict BMI would be 33.5 years. Now we've looked at quite a few histograms and we've talked about them, but how exactly do we use them? We saw that they can help us identify anomalies in the data, which is awesome, but we mostly use them to identify the distribution of the data. You can think of distribution as the shape of the data. And when building models and making predictions, we typically want our data to have one of two shapes: the normal shape or the uniform shape. This histogram shows the shape of a normal distribution, which is sometimes called a Gaussian distribution. And when people say bell curve, this is what they're talking about. It kind of looks like a bell. Now, this distribution occurs a lot in nature. It also has some really great statistical properties that make it like perfect for models. And unless you have a good reason why your data should have some other shape, you want it to have this shape. All right, it's symmetrical. The hump is centered over 0. When the hump is over 0 and it has this spread between like -4 and +4, we call it the standard normal distribution. Now, technically, the standard normal distribution has mean equals 0 and standard deviation equals 1, but for now, I want you to think that the hump is centered over 0 and the values are spread between like -4 and +4. Next week, we're going to learn a few ways to transform data from a different shape into this one. Another cool thing to know about the normal distribution is that like 95% of the data is between -2 and +2. And that's a great simple rule of thumb that will come up a lot. 95% of the data is between -2 and +2. In a normal distribution, the mean is right in the middle of that hump. And hey, look at this. The mean, median, mode, middle are all in the same place. All of the measures of center that we talked about are like right in the same place. The second most important shape for us to recognize is the uniform distribution. Notice how it's basically a big rectangle, flat across the top. This uniform distribution goes from 0 to 1, and typically that's what you want. Next week, we're going to learn a few ways to transform data from a different shape into this shape and set it between 0 and 1. Next thing, notice that the mean is right in the middle. Even better, the mean, the median, and the middle are all right in the center of the rectangle. But since the rectangle is flat on top, there is no mode for a uniform distribution. However, all of the measures of center that do exist are the same. And that's what we are really looking for when it comes to data shapes. When all of the measures of center are the same, it doesn't matter which measure of center you pick, and that's how you get the best predictions. These two work great for what are called continuous features. Don't worry too much. We need to talk about what's called a discrete feature. Now, discrete means it can only be specific values, like what color hair does a person have? There are only so many colors of hair, right? You can have, it's like black, brown, red, blonde, white, pink, purple, green, whatever. There are specific colors. Or in our data, a person either has diabetes or they don't. Nobody has 0.3 diabetes, right? That doesn't make any sense. That's what discrete means. A discrete feature can only take specific values. Now, for those features, there is no such thing as a mean. You can add up all the hair colors. You cannot add up all the hair colors and divide by the number of people. That doesn't make any sense. And there's no such thing as a median. There's no such thing as a middle. The mode is really just the common value. Like in this data, the mode of the outcome column is 0. Most people don't have diabetes. When faced with this kind of feature, a binary or categorical feature, it's best if the data looks like a uniform distribution where all the bars are the same height. Next week, we'll find a couple of ways to change data like this, where they're not the same height, to make them the same height.
That wasn't so bad, right? I mean, you've just learned a bunch of statistics without having to do any math at all. There's a link to this week's project in the description below. And this week it's all about histograms. You're going to be looking at histograms. You're going to identify which features look like normal or maybe uniform distributions. You're going to identify which ones you might want to change before modeling. You're going to choose measures of center, and you're going to make predictions, and you're going to estimate how wrong your predictions might be. Go ahead and try the project. My solution is there too. But remember, just because I did or said something doesn't mean it's the best way to do it. This is all about forming your own reasoning, your own approach for thinking about this and solving these problems. I absolutely encourage you to share your solutions with one another. and to leave your questions in the comments and to answer each other's questions. Now, if you learned something from this video, please give it a like. And if you want to keep learning with me, go ahead and subscribe. Now, next week, we are getting into pre-processing and exploratory data analysis. Now, that means changing the shape of our data to make it better for machine learning, and it means figuring out like what's due and values are missing. It means taking the features we've already got and using them to build more informative features. I mean, we're going to look for relationships between features, so like how do glucose and blood pressure affect one another? And we're going to practice showing this stuff to other people using charts and getting people to pay attention when we're telling them about the data. Now that video should pop up here, and I'll see you next week.